So we can obviously do a lot of analysis on signals that we might receive on a sensor, signals that we might get on a microcontroller like on our Arduino. And we'll start with some of the basics. And so signals will often have some static content to them, or some content with zero frequency. And I really think of that as a DC offset to my signal. So if I think of effectively having an average in here, so if I took the average of all of those points, right, that difference above zero would be my DC offset. And a way to write that mathematically is that the mean y bar is going to be the integral from some time t1 to some time t2 of my signal y of t dt, and I'm going to divide that by that time period t2 minus t1. This is really just taking the average. And if I have a periodic signal, and really this definition is most appropriate for a periodic signal, I might go from 0 to capital T, my period of my signal there. But I can apply the same basic concept of this DC offset to any signal that I might have. And DC offset is important primarily because I often want to remove it. And this could be anything from something as simple as just wanting to center something on your oscilloscope display, but also if I'm trying to actually analyze my signal and it has some kind of DC bias to it, oftentimes that comes from some drift in my sensor. It could come from a lot of different reasons, and oftentimes I just want to remove that and basically bring my signal back down to have an average of 0 so that I can better analyze it using the techniques we'll talk about later in this class. And then finally, believe it or not, this random collection of dots is actually a sampled version of the signal that I just showed you. And I can calculate DC offset for a sampled signal in addition to a continuous signal. The definition I gave you earlier was for a continuous signal, but the definition of the DC offset, or the mean of my signal, for a discrete signal would look something like this, discrete or digital. So in this case, I've replaced my integral with a sum, and I divide by that number of samples that I'm using in this summation to create the average. Now, once again, this makes the most sense for a periodic signal, right? Discrete signals can be periodic too. So DC offset gives me a sense of the static portion of the signal. If I want to get a better sense of the dynamic portion of the signal, I can use a metric called root mean square. And root mean square of a particular signal in this case is that y of t is 5 sine t. So y RMS is going to be equal to the root of the mean of the square of the signal. And for periodic signals, we can use that first time t1 as 0 and t2 as capital T, or the period of our periodic signal. And this is really the best approach to use if you're looking at RMS of a periodic signal. And we can look at what this means graphically as well. So in this case, my red signal here is my 5 sine of t. My blue signal will be the square of that, or 25 sine squared t. And obviously once I have the square of that, I'm going to have no negative content to that signal. And I go up to an amplitude of 25. And my yellow signal here is my RMS value of my dynamic signal. So it looks static, right? It's a signal number that I get out of this, but it's measuring kind of the amplitudes of my dynamic signal, giving me some sense of the variation in this dynamic signal. Of course, I can also have a root mean square for a discrete signal. In that case, I'm replacing that integral with a sum again. But I still have my root, I still have my mean, in this case 1 over n, where capital N is my number of samples in a period, for example, and then I have the square of all of the samples within that range of my discrete signal. And a great example of RMS values is looking at line voltage, or the voltage that you have, the voltage signal that you have in your wall that you're plugging in your laptop to, for example. So you think of that as a 120 volt or 110 volt signal probably, but that signal is actually something like 170 sine 60 times 2 pi times t, right? It's a 60 hertz signal, right? I'm actually using omega here, so I multiply that by 2 pi. And 170 is actually my amplitude, and that's in volts, of course. But the RMS value of that is 120 volts. And that's what you think of when you think of the voltage on your wall socket. But that's not the amplitude of the signal, that's the RMS value.